Walking back to where we've been as far as solving quadratic equations, we first learned to solve quadratic equations by factoring. You all were pretty good at factoring polynomials. If we can set a quadratic equation equal to 0, factor the other side, by the zero product property, we know that each factor itself can be set equal to 0, and you could solve those two simple equations. We also found that some quadratics could be solved relatively easily by taking the square root of both sides. However, we ran into some tougher situations, in particular cases where we could not factor the quadratic, and it wasn't easy to square root both sides. So we learned a method called completing the square to tackle those types of quadratic equations. It turns out that that was a bit of a challenge for quite a few of my students, not really a way that they were very comfortable with. And if there was a different way to solve those more challenging quadratics, I think they'd be really happy to find out about it. So we introduced the quadratic formula in class last week. Quadratic formula is kind of like duct tape for quadratic equations. It'll solve anything. No matter how simple or how complicated the quadratic equation is, the quadratic formula will solve it. And so the quadratic formula, as long as we have a quadratic equation set equal to 0, the quadratic formula will produce the two solutions. X equals the opposite of b plus or minus the square root of b squared minus 4 times a times c all over 2a. So let's take a look at a couple of examples. First one that's relatively simple, just so we can get the basics of solving using the quadratic formula. First off, we look at the equation, is it equal to 0? It's our first most important step, is to make sure that we have 0 on one side of the equation, and we do. So now we're going to go ahead and locate our a, b, and c values. A is our multiplier on x squared, b is the coefficient on x, c is the constant. So in our case, a is equal to 1, b is 6, and c is 8. So now let's take those a, b, and c values and insert them into our quadratic equation. X equals the opposite of b, which is the opposite of 6, plus or minus the square root of b squared, which is 6 squared, minus 4 times a, that's 1, times c, which is 8. All of that is in the numerator, over 2 times a, which is 2 times 1. Now in 2 steps, we're going to simplify this down from something that looks pretty horrible to something that's pretty manageable. So negative 6 plus or minus the square root of 6 squared is 36. Now, here's a big stumbling block for a lot of my students, and a method they've used to smooth that out. Rather than writing the minus sign right away, they're going to take this value, the 4ac, and treat it as if that's negative 4 times a times c. And then write the answer with its sign, whether positive or negative. They'll always get the correct sign here. So negative 4 times 1 is negative 4 times 8, that's negative 32. So inside our radical, 36 minus 32 all over 2. So negative 6 plus or minus the square root 4 over 2. So in just 2 steps, we went from this mess to something that's much more easily handled. So negative 6 plus or minus the square root of 4 is 2 over 2. All right, and when we reach this point, it's important to keep in mind that this equation is going to produce two solutions. A quadratic equation will have two solutions. This formula will generate both of them. But we're only solving one equation. What's going on here? Well, remember we have this plus minus sign. Right? What that really indicates is that we have two different equations here. X equals opposite of b plus square root of b squared minus 4ac all over 2a, and x equals opposite of b minus the square root of b squared minus 4ac all over 2a. Exact same equation, except for one thing, the sign. It's already going to take us half a sheet of paper to solve one problem. Why would we want to do this twice if the only difference is one sign? So somebody a long time ago, wise math guy or math girl, said, look, why don't we combine that plus minus? And then we'll just write this once, and we can split it up when the time comes. Well, this looks like a good time to do that split. So we're going to write x equals negative 6 plus 2 over 2. And we'll write x equals negative 6 minus 2 over 2. Now we'll take this one quadratic split into two separate equations. So negative 6 plus 2, that's negative 4 over 2. Negative 6 minus 2, that's negative 8 over 2. So x equals negative 2 or x equals negative 4. So I picked this example for my students on purpose. Relatively simple. It turns out to have two integer roots, and to be honest, there's an easier way to solve this. They probably would rather solve this by factoring than go through the time and trouble to use the quadratic formula. I wanted them to see the steps of walking through the formula and not be distracted by having to simplify radicals. But now that we've got that done and out of the way, let's look at a problem that it does make more sense to use the quadratic formula for. X squared plus 3x minus 5 equals 0. Or a is 1, b is 3, c is negative 5. Take a minute, go ahead and pause the video. You set up the formula. So x equals the opposite of 3 plus or minus the square root of 3 squared, and then minus 4 times a, which is 1, times c, which is negative 5, all over 2 times 1. So negative 3 plus or minus the square root of 9, negative 4 times negative 5, that's positive 20, over 2. So simplifying inside the radical sign, 9 plus 20 is 29. Our job now is to simplify that, but 29 doesn't have any perfect square factors. In fact, it's prime. It doesn't have any factors at all except itself and 1. This is a perfectly acceptable answer for this problem. X equals negative 3 plus or minus the square root of 29 over 2. Now, if we were applying this in a word problem, we would go ahead and take that square root of 29, get a decimal approximation for it, simplify this out and get a numerical value for x. But for right now, our exact value is perfect. The second part of the section is using the discriminant, which is the value of the expression underneath the radical sign, b squared minus 4ac, in a quadratic equation. The discriminant will let us know the number and type of solutions. If the discriminant value is greater than 0, if it's positive, we have two real solutions. If it's equal to 0, that's a case where we have a perfect square trinomial. Both factors, if we were to factor it, would be equivalent. One real solution. The vertex is on the x-axis. If the discriminant is negative, though, back in Algebra 1, we used to say there were no real solutions. Well, now we know that there are two imaginary solutions. Let's take a look at using the discriminant. In our example equation, x squared minus 6x plus 10 equals 0. A is 1, b is negative 6, c is 10. So using the formula, b squared minus 4ac, that's negative 6 squared minus 4 times 1 times 10. 36 minus 40 equals negative 4. So our discriminant is negative. This tells us that we have two imaginary solutions. So when we hear this idea of imaginary solutions, let's walk back and think about what it is that we're talking about. We know that a quadratic, if we graph it, it might cross the x-axis once. It might have its vertex on the x-axis, just touching the x-axis, crossing the x-axis once rather than twice. Or I could have a situation such as this, where the vertex is not on the x-axis and it opens either up or down in that same direction. This quadratic will never touch the x-axis. It has no real solutions. How do we deal with that? Well, let's take a look using the quadratic formula. X equals opposite of b plus or minus square root of b squared minus 4ac all over 2a. And using our example problem from above. X equals the opposite of negative 6, which is positive 6, plus or minus square root of negative 6 squared minus 4 times 1 times 10. That's the example we just did, over 2 times 1. All right, so this is the issue that we ran into before. How do we take the square root of a negative number? It's not defined in the set of reals. Well, we know that if I have a radic hand, I can split it into two factors, and each can get its own individual radical sign. Well, in this case, the square root of negative 4, I'm going to go ahead and break that down into the square root of 4 times the square root of negative 1, which remember the square root of negative 1 we call I. Square root of 4 is 2, so the square root of negative 4 we say is equal to 2I. So now, x equals 6 plus or minus 2I over 2. I can factor out a 2 from each of these, 3 plus or minus I would be my solution. Those are my two imaginary solutions. Lastly, let's take a look at applying this to a word problem. So Olympic diver, the platform 32.8 feet above the water, initial velocity of 4 feet per second. How long is the diver in the air before hitting the water? So h equals negative 16 t squared plus 4t plus 32.8. A is negative 16, B is 4, C 32.8. Let's set this up. Negative 4 plus or minus 4 squared minus 4 times negative 16 times 32.8, all that under the radical, or 2 times negative 16. So to our calculator we go. Negative 4 plus or minus, underneath the radical we have 16, and then 2 negatives multiplied, and then times a positive. This is going to be a positive result. So 4 times 16 times 32.8, 2099.2, all over negative 32. So underneath the radical now, 2115.2, when we square root that, we get 45.99. Basically 46 for our purposes. Now let's split this in two. Negative 4 minus 45.99 all over negative 32, or negative 4 plus 45.99 over negative 32. So negative 49.99 over 32, or 41.99 over negative 32. Well, this answer is going to give us a negative time value, which makes no sense. So let's try this one. 49.99 divided by 32 equals 1.56 seconds. So the diver's in the air about 1.5 seconds before hitting the water.